Mathematicians in the early part of this millennium became quite adept at approximating the area of irregularly shaped objects using a technique that even the Greeks had imagined but did not formalize. Hi, my name is Jason Rosenberry, and in today's lesson is learning to use the rectangular approximation method to estimate finite sums. Let's start with an example. Finding the distance traveled when velocity varies. A particle starts at x equals 0 and moves along the x-axis with velocity v of t equals t squared for time t greater than or equal to 0. Where is the particle at time t equals 3? So let's back up a step and let me first show you the relationship between distance, how far the particle or an object travels, in relation to its rate. So let's look at a simpler example. On the x-axis, let's call that t for time, and in this case let's measure this in hours. And the y-axis, let's let that be the rate, or as we know, rate is also known as velocity. So here's some velocity function v of t. For our simple example, let's make the velocity function a constant function. Let's say that velocity is 60 miles per hour. Now, if I were to ask you, how far did you travel in 5 hours traveling 60 miles per hour? You know that 60 miles per hour, 60 times 5 is 300, so we would have traveled 300. Let's look at that geometrically. Again, let's let the t-axis, the x-axis, go from 0 to 5. And let's say that v of t is 60 miles per hour. Well, do you see the relationship between our previous answer of 300 miles and our figure? We see that if we take t equals 1, 2, 3, 4, 5, multiply that by the height of the rectangle, 60 miles per hour, the area of this rectangle, or the area under the velocity curve from 0 to 5, corresponds with the total distance traveled. This case, our velocity function was a constant function. Now, the current example, we can see that our velocity function is not a constant function and therefore it varies. So let's go ahead and come up with a way of approximating this answer. So looking at the upper left-hand diagram, we've come to the conclusion that our answer, the total distance traveled by our particle, is the total area under this velocity curve, the area under the v equals t squared curve, from 0 to 3. And if you look at that region, that is not a nice geometric figure like a rectangle or a triangle where we would have a formula that we could use. Therefore, we need to take this area and divide it up into equal rectangular subintervals such that we could add up the area of each rectangle to come up with an approximation of the true area. So as you can see, we're taking the distance from 0 to 3 and we're dividing it up into 12 equal rectangles. So if we say delta x, being the width of each rectangle, is equal to b minus a, 3 minus 0, divide by n, the number of rectangles, we can see that we end up with 3 over 12, or delta x is equal to 1/4, or 0.25. So each of our 12 rectangles has a width of 0.25. Now let's switch over to the right side diagram. There we've taken our area and we've divided up into 12 equal rectangles where the width of each rectangle is 0.25. Now let's come up with, how do I figure out how tall each rectangle would be? So again, we've zoomed in on a particular interval. In this case, this diagram, we've zoomed in on the 0.5 to 0.75 interval. And as you can see, there are 3 ways of obtaining a rectangle height. We could either use the left endpoint to approximate the rectangle height, or we could use the right endpoint to approximate the rectangle height, or in this case we will use the midpoint of each interval. So if we take 0.5 plus 0.75 and divide by 2, that midpoint would end up being equal to 5/8. So now let's look at our last chart. Let's actually run through the process of adding up the area of each rectangle. And what you're seeing here in great detail would correspond to the first 4 rectangles of our approximation. So looking at our very first rectangle, I know you can barely see this rectangle, but there is a rectangle there. It is going from 0, and remember each rectangle is 0.25 units wide. So our first rectangle would go from 0 to 0.25. The midpoint would be 1/8. Now using that midpoint, we will get the height by plugging that midpoint into the function t squared. So 1/8 squared is 1/64. And there you have the information that you need to find the area of your first rectangle. Area of rectangle is base times height. The base, which is the case for all rectangles, is 0.25. The height of your first rectangle is 1/64, and multiplying those together, we get 1/256. So this fraction, 1/256, is the area of our first rectangle. Now let's take a look at the area of the second rectangle. The second rectangle covers the subinterval 1/4 to 1/2. We locate the midpoint of that subinterval. That midpoint is 3/8. We now evaluate the function at that midpoint, so substituting 3/8 into the equation t squared for t, we get the function value 9/64, which would be the height of our second rectangle. Now to find the area, we take the height of the rectangle, 9/64, times the width of the rectangle, which is 0.25, which is the width of all rectangles, giving us an area of 9/256. So that's the area of the second rectangle. We're going to continue on with this. Third rectangle, fourth rectangle, up to the 12th rectangle. And when we add those 12th rectangle, and when we add those all up and round off to the nearest 2 decimal places, we can see that the approximate area under the curve t squared from 0 to 3, using midpoints to determine the height of the rectangle, is 8.98. So our conclusion would be that this number, 8.98, approximates the total distance traveled by the particle, so we can conclude that the particle moved approximately 9 units in 3 seconds. Again, what we did in that first example was use the midpoint to find the height of each rectangle. Then we summed all the areas. This is one rectangular approximation method, and we can use the abbreviation RAM for rectangular approximation method. So when using the midpoints like we did here, we could abbreviate that MRAM, midpoint rectangular approximation method. As I mentioned earlier, we could use the left endpoint or the right endpoint to obtain the height of the rectangle, and there again we could call that LRAM or RRAM if you were to choose to use the left endpoint or the right endpoint. Let's try another example. Use rectangular approximation method to estimate the area of the region enclosed between the graph of f and the x-axis for x on the closed interval from a to b. F of x is x squared minus x plus 3, and it looks like we're traveling from 0 to 3. So again, let's use 12 rectangles to approximate the area under this curve from x equals 0 to x equals 3. Again, our function was f of x is equal to x squared minus x plus 3. Let's find the width of each rectangle. So delta x, the width of each rectangle, would be b minus a divided by number of rectangles, and again we get 0.25. So now we begin the process of finding the midpoint of each interval, plugging that midpoint into the function to get the corresponding areas. So here we go. The area will equal, what's the width of the first rectangle? 0.25. and we're going to multiply that by the height of the first rectangle, which we'll obtain by plugging this midpoint into the function. Well, that midpoint is 0.125. So we'll take 0.25 times f of 0.125. And then we'll add that to second rectangle. Again, the width is 0.25 times its midpoint is 0.375. We will plug that into function f to get that next rectangle's height. So 0.25 times f of 0.375 plus, and we will continue on, plus dot 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 until we get to the last rectangle, and that last rectangle would be, the last term would be 0.25 times f of last midpoint, and that last midpoint, our last midpoint would be 2.875. 2.875. So plugging those values into the function, get the corresponding heights, multiply each by 0.25 to get the area of each rectangle, and then adding them all up will give us an area of approximately 13.5. Your textbook mentions that there are free programs out there for your graphing calculator that you can install into your graphing calculator for these rectangle approximations. Here's the same problem that we just finished. In this case, I used TI-84 to go ahead and approximate the area. So I told this program, using 12 rectangles, the lower bound being 0, the upper bound being 3, and the function being f of x equals x squared minus x plus 3, you can see that this computer or calculator program gives you the left endpoint, using the left endpoint as determining the height of the rectangle, the right endpoint, and also midpoint. So as you can see, by pencil paper we came up with 13.5, and as the calculator shows you, it should be about that, and it is 13.484375. The one labeled trap for trapezoid, that's a future section coming up on using trapezoids to approximate the area under a curve of a function. We can also use rectangular area approximations, RAM, to estimate volumes. Let's do this for a sphere. Our example says, estimate the volume of a sphere of radius 4. So let's start with the equation of a circle with radius 4. So looking at our first picture, if we take the x squared plus y squared equals 16 equation of a circle centered at the origin with radius 4, solve that equation for y and choose the positive root, that gives us the equation y equals the square root of 16 minus x squared, which corresponds to the top semicircle, the top part of the circle, from negative 4 to 4. Now imagine rotating that arc, rotating that curve around the x-axis, and doing so it would then form a sphere of radius 4. Now imagine taking that sphere and dividing it up into equal subpartitions. And again, each partition, in this case, unlike the last problem, we were dividing area up into rectangles. Here we're dividing volume up into cylinders. And again, look at these cylinders. They're kind of located on the side. They're oriented sideways so that the bases, top and bottom, are actually to the left and to the right. So delta x will now correspond to the height of each cylinder. So just like we did last time, we found the area, we approximated the area by adding up areas of a bunch of rectangles. We will now approximate volume by adding up the volume of a bunch of cylinders or discs. In this case, we're dealing with cylinders, so let's start with the volume formula for a cylinder. volume of a cylinder would be pi r squared h. And now let's take a look at each one of these cylinders. So I'm going to start with the one here on the right side. Again, we've established that delta x will be the width of each cylinder, or in this case the height of each cylinder, and the more subdivisions that you would have, the smaller that amount would be. So we've taken care of the h in our volume formula. H is simply delta x. Let's talk about the radius of each cylinder. Well, again, I'm going to focus on this left side or this right-sided disc. If we were to again think of these 2 points here as our 2 endpoints, just like the left endpoint and the right endpoint of our rectangle, remember what we did? We chose the midpoint. We plugged the midpoint into the function that got us the height of the rectangle. Well, in this case, we're going to choose this midpoint. We're going to plug that midpoint into this equation, which then gives us the radius of that cylinder, which we need with our volume formula. So making that substitution, volume will equal pi times radius squared. So that would be square root of 16 minus x squared times delta x. And take a look at what happens with our formula. The square and the square root would now cancel each other out. So that leaves us with volume would equal pi times the quantity 16 minus x squared times delta x, where again delta x is completely up to you. That would be the number of cylinders that you're dividing your sphere up into. And again, looking at our chart, as you increase the number of cylinders, or in this case that they're calling the number of slices, number of discs, if you increase the number of discs, there you're causing delta x to get smaller and smaller and smaller, allowing you to have more subdivisions. And the more subdivisions that you have, you can see that your volume is getting closer and closer and closer and closer to the true volume of the sphere of radius 4. Now it is time for you to try a problem. Volume of a nose cone. The nose cone of a rocket is a paraboloid obtained by revolving y equals square root of x for the closed interval 0 to 5 about the x-axis. Estimate the volume V of the nose cone by partitioning from 0 to 5 into 5 subintervals of equal length, slicing the cone with planes perpendicular to the x-axis, at the subinterval's left endpoints, constructing cylinders of height 1 based on cross sections at these points, and finding the volumes of these cylinders. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. So here's a diagram of our situation. We're taking the graph of y equals the square root of x and rotating that curve around the x-axis to simulate the nose cone of our rocket. And we're taking the distance 0 to 5, breaking up into 5 subintervals, such that we're to use the left endpoint to determine the radius of each cylinder. And we're also told that delta x for each cylinder, or the height of each cylinder, is 1 unit. So let's start with our volume formula again. A volume of one cylinder is pi r squared h. And now we'll make some substitutions. Pi stays pi. What will use to determine the radius? Well, we're going to plug each left endpoint. That means 0, 1, 2, 3, and 4. We're going to plug those values into this formula and then turn around and square it. So where do we get our radius from? Radius will be found by taking the square root of x and squaring it and multiplying that by h. So one last simplification, volume would equal pi times the square root of x squared, which is just x, times h, or delta x, which in this case is 1. So we will use volume equals pi times x. And now we'll use all left endpoints. So our volume will equal pi times, and remember, adding up the volume of each cylinder. So the first value that we use is 0 plus 1 plus 2 plus 3 plus 4, and we approximate that to 3 decimal places. We get 31.416. 31.416, and the units would be cubic feet as an approximation of the volume of this nose cone. Another use for RAM method is in approximating area under a curve given a graph and some numerical data. Let's try an example. Cardiac output. The following table gives dye concentrations for a dye concentration cardiac output determination. The amount of dye injected in this patient was 5 milligrams. Use rectangles to approximate the area under the dye concentration curve, and then go on to estimate the patient's cardiac output. So here's the data. We'll let the x-axis be time t in seconds after injection, and we'll let the y-axis be the concentration. Plotting these points and drawing a smooth flowing curve through these values gives us the following graph. So the first part that we need to solve is find the area under this curve from 2 to 24. And as you can see, we're going to use 11 rectangles. This will be the first rectangle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 rectangles. Delta x, or the width of each rectangle, would be 2 units, and we'll go ahead and use the midpoint technique to find the height of each of these rectangles. So for instance, our first midpoint would be 3, and using 3 we'll go up till we hit the graph, we'll go across to the left side, and we'll approximate that to be about 0.25. So our first rectangle would look like that. The second rectangle, we'll use a midpoint of 5, and we'll go up till we hit the graph, which is right here at 1. So the second rectangle would look like this. And we'll continue this process. Again, we'll choose the midpoint of each rectangle, each interval, go up till you hit the graph, and then approximate about what that value is, and that would be the height of that corresponding rectangle. We'll now add up the area of all of these rectangles. So our area would equal 2 times the following. 2 is the width of each rectangle. Now we have the corresponding heights of each rectangle. The first one is about 0.25, plus the second one 1, plus 2, plus 3.25, plus 4 plus 4, plus 3.5, plus 2.25, plus 1.25, plus 0.75, and plus the last midpoint, the last height of the last rectangle is 0.25. So performing that arithmetic, adding those up and then multiplying by 2, we get an area of 45. So there was the answer to the first part. Find the total area under the curve from 2 to 24. And now the follow-up question is, go on to estimate the patient's cardiac output. And we're told in the problem that the patient was injected with 5 milligrams. So this patient's cardiac output, let's call it CO, would equal the 5 milligrams per liter that the patient has divided by the total, which is the area under the curve that we found in the previous part. And this would give us, in terms of milligram liters per second, and we want to convert this in terms of milligram liters per minute. So we'll multiply that by 60, and that gives us approximately 6.7 milligram liters per second. In this lesson, we explored estimating finite sums using RAM. Be sure to work the exercises that your teacher assigns, and we'll see you next time.